Okay. Yeah. Sorry for the delay. We had some technical problems as usual. Okay, today we tell you about Gamecube hacking. We will tell you a bit about Gamecube hardware, some more details about the Gamecube hardware, some way to get your own code onto the Gamecube, how the boot process works, a bit about encryption and stuff, and finally we tell you about Linux and possibilities of extending the whole system. Yeah, the Gamecube was codenamed Dolphin. It's a console by Nintendo, I think you know this. It was released in Japan in end of 2001 and in the USA some months later. Yeah, it's counted to the 128-bit console generation, but yeah, that's what the marketing guys say. The initial price was $199, which was quite competitive to the Xbox and the PS2, for example. Now you can get the Gamecube as cheap as €99 or even cheaper. So it's a really cheap console compared to other systems. The Gamecube is built around the Gecko CPU. That's the PowerPC-based CPU at 486 megahertz. It's big endian, as usual, for a PowerPC CPU. The CPU itself has a bus interface, a typical PowerPC bus interface, 64-bit, sorry, at 162 megahertz. Yeah, gives 1.3 gigabyte per second to the marketing guys. It has a nice 32 kilobyte instruction cache, the same size data cache, and a large second level cache. Yeah, well, large for this type of system. The GPU, which does all the graphic stuff, was made by ArtX, was now bought by ATI. It has about 2 megabytes of embedded frame buffer memory and 1 megabyte of high-speed texture cache embedded into the core on the same die. And the GPU supports all modern 3D features. Well, at least of that time in 2001, it was very modern. The storage medium is based on DVDs. It's mini DVDs, so it's 7.5 centimeters. But it's of course copy protected, and it's a proprietary extension to the DVD standard. We can show you. That's a typical game. It allows 1.2 gigabytes per disk. The Gamecube doesn't have any standard interfaces like the Xbox. There's no USB or something. Most interfaces are proprietary. For example, the serial controller ports, which are N64 compatible, or the memory card slots and 2 serial ports. They are called serial, but in fact they are SPI-like. It's called the XE bus. And there's finally a high-speed port made for SD-RAM extension or features like the Game Boy player. It can be attached there. It has an SD-RAM styled interface, so it's parallel and high-speed. That's the block diagram of the Gamecube. You see the flipper in the middle. Connected to the flipper is the CPU on the top and all the different interfaces. For example, for the controller, for things like the broadband adapter, which is a network adapter, memory cards. Then there's the DVD bus attached to the flipper, 16 megabytes of additional SD-RAM, 24 megabytes of high-speed, yeah, it's called SRAM, but it's not real SRAM, I'll come to that later. Then there's the video output, of course, connected to the GPU, and yeah, that's it. The CPU itself is called Gecko, that's the code name. It's a very close relative to the PowerPC 750CXE, or called G3. It's used in the G3 Apple computers. It's clocked at 486 megahertz. Yeah, it has a standard PowerPC bus interface, and all memory access go through the flipper, but they are very fast anyway. The CPU contains a full-featured MMU, which is very important since we want to run Linux, of course. drawbacks are that there's no real debugging interface. There's not even a normal serial port to output debug information. There's no JTAG or something. Well, at last it's not known if there is any and how it could be used. The whole system is not cache coherent. If you program something for the GameCube, you have to take care of the cache everywhere. But the CPU was extended over the G3 CPU by special features like a DMA transfer to its log cache, which is very important in games, the write gather pipe, I come to that soon, and the paired single extension. The write gather pipe allows you to stream that data to memory. You can write any size words, bytes, words, half words to a fixed location, and the CPU will gather these write and collect whole cache lines and write them at once. So you get maximum bus efficiency for non-cacheable data like 3D geometry data, which is otherwise very inefficient to transfer over a bus because there are many different data with like bytes, words, and the write gather pipe collects them to maximum the bus utilization. The paired single extension is an SIMD extension. It's not compatible to the Altivec like on the G4. The G4 came later and came from Motorola. So it's a proprietary extension. It allows two 32-bit float operations per cycle, and that's a speed increase over the very fast FPU. It's used in some games for local lighting because the 3D hardware is a bit limited, so the CPU can do tasks like local lighting or 3D transforming or something. The debug interfaces, it's a bit sad. The Gecko was made with special debug interfaces. It was a design criteria from Nintendo that it could be tested at the full speed. So they have a special debug interface which allows a full speed production verification. But unfortunately, there's no information available about this, and it looks like on production board, these boards we can buy in GameCubes don't have any debug ports available. It looks like there were some boards which had these ports, but all boards I've seen don't have any connectors which could be JTAG or anything else. It's a bit sad because programming, it makes it trial and error, and it would be nice if there would be a way to debug, but there is no real. I don't think this is made for security reasons, but I think it's what to reduce the costs and so. The flipper itself is a custom graphics processor. It's not related to any ATI processor. There's a sticker on every GameCube called Graphics by ATI, but ATI bought ArtX, the company which made the chip, after they have already finished the design of this chip. So it isn't related to any chip of the AT. The flipper contains embedded RAM. The texture cache, for example, is very fast. It can do 10.4 gigabytes per second. And it had state-of-the-art features in 2001. Nowadays, it doesn't look that good anymore, but it was. Some features are real-time texture compression, the S3TC like on DirectX, 8 hardware lights, the usual stuff like anisotropic filtering and so on. Special thing about the flipper is that the performance is very predictable. So you can calculate how many polygons per second you can push through it if you know how many lights you are using and so on. So it's a very predictable hardware, which is good if you want to maximize the performance of the chip. But unfortunately, the vertex processing especially is very hardwired, and there is no way to do custom effects. They have to be pre-calculated by the CPU. The pixel pipeline is a bit more flexible, but is still limited compared to pixel shaders or something. It supports up to 16 stages and 8 textures. Yeah. The Flipper has some interesting features, like the relative easy access to the Z buffer, for example, for depth blur effects or indirect textures for glass mapping and stuff. But I guess nowadays they are normal features. The performance of the Flipper. It wasn't made to provide top speed peak polygon rates, but to deliver a decent performance in real games. So be careful when you compare the numbers. For example, Nintendo gives 6 to 12 million polygons per second. They're quite conservative. Games like Star Wars actually do these 12 million polygons per second and even more in average. So yeah, be really careful when comparing these numbers. Just better look at the games and judge for yourself. Yeah, the external interfaces of the Flipper are mapped into the CPU's address space, which makes sense since the CPU has to do all memory accesses through the Flipper. There are peripherals like the DVD drive, which has a separate firmware, the controller ports for the game controllers, these XC ports, and the high-speed port. They are all connected to the Flipper, and DMA is supported, fortunately, for the most operations, which is good for the performance, since the CPU doesn't have to wait for the peripherals. Yeah, RAM is often a bottleneck in games, because especially games do lots of random access to the RAM, and usual RAM like SD-RAM isn't very fast at random access. They have all paged access, and the Gamecube tries to remedy this because it has 24 megabytes of something like SRAM styled RAM. This has 10 nanoseconds random access latency, which is very good compared to other types of RAM. It's not really SRAM, but it behaves like it, but it requires only one transistor per memory cell. Real SRAM requires 6 transistors, and it would be too expensive to put 24 megabytes of it. There are additional 16 megabytes of RAM, which is usual SD-RAM. It's used for audio only, but it can be used by the CPU as well. It's not directly accessible, it's not memory mapped, but it can be DMA'd into the RAM and then be used. Some games, and Linux too, use it. Thanks to the MMU, it's possible to memory map or to fake a memory mapping of this using swapping. And some games really use it because they need more RAM, but for example, slow RAM for game stuff and not for the graphics. It's quite usable. The mass storage itself is a DVD-ROM. It's proprietary, but it's very DVD-like. The drive was made by Matsushita, and it has a very interesting method of copy protection, which can be read in Nintendo's patents. It's available at the US Patent Office, so if you're interested, you can read it. It used to be uncracked because the drive's firmware just refuses disks without that protection. So you cannot, if you modify, for example, the boot ROM, you can't read normal DVDs. The DVD's firmware just doesn't allow it. But yeah, it's not really true anymore. About 1 week ago, a chip appeared which was able to read copied disk or burned disk. We don't know yet how they made it. It looks like they exploited the DVD's firmware using a backdoor comment. We'll see. But usually it's not possible. It's not a question of the software running on the Gamecube, it's a question of the DVD firmware. But that shouldn't prevent anyone of trying to run code on it, just because we can't boot DVDs. So 2 software hacks have appeared. The first software hack came in the beginning of 2003 and it was called the PSO hack. And later there was a hack using Datel's action replay, which can be abused to patch code into memory and load it. The advantages are that they don't require any hardware soldering or stuff, but each time you want to boot a new binary, you have to reboot the cube, have to go through all the game introduction and so on. So it's not really the best way. But there are hardware hacks possible, which I'll describe later, the IPL replacement, for example. The PSO hack was the first available hack for the Gamecube. It involved a game called Phantasy Star Online. It's an internet role-play game. And it contains the possibility to download code fragments from the server to check against cheats. So if they know that some cheats, for example, using the action replay are used, they can push code to the clients, to the games, and the code will then check for the cheat. That was how it's supposed. But this protocol was encrypted, but it was hacked for the Dreamcast, and later this hack was ported to the GameCube. And now it was we were able to upload own code to the GameCube because there are tools like PSO load or PSUL, which emulates the server using DNS faking and upload own code, which then loads the code you want. It requires a broadband adapter, it's a network adapter, it's available in stores, or at least was available in stores, even in Germany. And it's relatively easy to get and use. Okay, you need the game and the BBA, but then it's only a matter of software. But it really slows down the development cycle because it takes about 2 minutes to boot through the game. You have to go through all the introduction again. Each time you have a bug in your code and need to reboot. Then Samson, a guy, made something using the action replay. The action replay is made by Datel. I think most of you know these action replays by Datel. They allow entering encrypted cheat codes for games to enable infinite life or something. Datel knows how to make authentic disks, so they are able to produce real game disks. We don't know how, but they are able to do this. And cheats are basically patches in memory. So they patch the game, and but the encryption was reversed, and now it was able to patch arbitrary data into memory, for example, own code, which would then be executed when the game started. So it was possible to upload or to patch some small loader code into memory, and the loader code then loads the binary from memory card or the BBA. It was a bit quicker than the PSO method, but still not perfect. Finally, it's possible to replace the boot ROM. It involves a hardware modification, and I'll describe this later in more detail. Yeah, the boot process is interesting because, of course, we want to inject our own code and don't run the Nintendo code. GameCubes don't have any parallel boot ROM like the Xbox or something. Instead, they have a serial ROM, which is contained in the real-time clock chip. And that real-time clock chip is on the XC bus. The XC is, as said, the bus where the memory cards are attached and the real-time clock. The BIOS is encrypted. It's possible to read the ROM very easily. The protocol is very easy, but the BIOS is encrypted. And the flipper translates memory accesses while the boot process to XC transfers the data, decrypts them, and sends them to the CPU. The CPU just do a memory fetch and receives the decrypted BIOS data. The CPU boots from FFF 00.100, like every PowerPC CPU, and the flipper memory maps the boot ROM there. Yeah, what could go wrong with this? Never reuse key streams, everybody said, but Nintendo did it, so they use the same key stream every time. It's just XORed against the payload. So if you have two different images of two different ROM, for example, PAL and NTSC, and XOR them together, you get the XORed plaintext, and now if one image contains zeros somewhere, you get the plaintext of the other image. So that was the first mistake they made, but it was even worse. Yeah, that's the ROM access protocol. It's very easy. Each column is one clock cycle. So you see first the address, which is marked as A here, is transmitted in 4 bytes total, with some stuffing left and right. And then after 32 bit cycles, the ROM responds with the data called D here. So on every cycle, 1 bit is transferred in each direction. It's a bidirectional bus. It has one line which goes to the GameCube and one line which goes to the slave device. So unused bits, they are marked as X here, are ignored. They are dummy bits. That would be no problem, but yeah, sniffing the bus while the boot process, no problem. It can be done with a logic analyzer or custom hardware. And if we look at the start, at the EXE transfers done at the start, the address sent will be marked as yellow. The encrypted ROM data, which comes back from the ROM, is marked green. And interesting data, I'll come to this soon, is marked in red. So here we see the first transfer. The address is marked as yellow. It's shifted 6 bits to the left, so it's 100. And on the next cycles, the ROM responds with the encrypted data. But on the next cycle, something very interesting happened. The zeros in the first access are just the dummy bits, which are sent when the flipper receives the bits from the ROM. So they can just be 0 or 1 or anything, they don't matter. But the flipper sends back data, and this data doesn't look as random as the data transferred from the ROM, but if you disassemble them, they are valid code, so it looks like the flipper does shift out decrypted data in the dummy bits. So that's really strange. Yeah, we see the CPU fetches instructions from 100 upwards. The ROM transfers the encrypted data to the flipper, but the flipper sends decrypted data as dummy bits, which is unrequired and completely stupid, but it does. So how could this happen? The flipper's EXE interface is implemented with a shift register. That makes sense because it's a serial protocol and we want to read the data parallel. So the data from the EXE bus is shifted in and the data to the EXE bus is shifted out. And now in the boot process, the encryption is done on the fly. So the decryption is done before the data enters the shift register. Now imagine what happened when the shift register never get cleared. The decrypted data will go into the shift register and on the next cycle it will be shifted out. And it just looks at it isn't cleared after each transfer, which is very, very stupid, but it's clearly a bug in the design. I don't know, maybe they didn't notice it, but it's unlikely because hardware gets really tested a lot. But maybe it was added in the last hardware revision of the chip. There are two big hardware revisions, and a new revision is on this chip, I guess, in the range of $1 million or something. And maybe they didn't want to afford a new mask revision. Or maybe they are just stupid, but I don't believe this because they were intelligent enough to build the rest of the chip, which is designed very well. Anyway, this helps us. Well, does it help us? We see that the last 4 bytes of each transfer are missing. We see the decrypted data 32-bit cycles after they come in. So in the boot process where 8 bytes are transferred in each transfer, this gives us only 50% of the fetched data. But fortunately, only the first 700 bytes are executed directly by the CPU. It's called the BS or bootstrap. The rest, the real stuff, is transferred using DMA blocks of 1 kilobyte. That's the BS2. That's the stuff you see when you switch on the Gamecube. So the last 4 bytes are missing, but we get 1020 bytes back, decrypted. Now we have the decrypted bytes and the encrypted bytes, so we can XOR them, get the key, and XOR our own code with that key and inject it. We need to make a hardware which emulates the ROM and replaces the original data with our new encrypted code, but that's possible. This code, which is easily fit into the first 1020 bytes, can then dump the rest of the read stuff into memory, from memory to the outside, and then we have even the missing bytes in between, the 4 missing bytes every block, because the roll loader, the roll BIOS is loaded into the RAM and then executed. So we just replace the start of the BIOS with our own dump code, and then we can XOR them. The first 700 bytes are still a problem because they are transferred in 8-byte blocks and we miss 50% of them. If we would have JTAG available, it would be very easy because we could just hold on the boot process and read the data directly from memory through the flipper, but JTAG isn't available, and the decryption is only one way. They increments each transfer. So you can't go backward, you can't re-decrypt data other than resetting the flipper. So this is a problem. But every second instruction is known in plain, so we could just patch in a jump. Yeah, where do we jump? Into memory, but then we have to place a dump code there. But that's no problem because we can inject code and put the dump code there, then reset the cube and let the cube jump into memory directly in the second instruction executed. Then we can fetch the rest like the CPU does, but this time transfer them to a PC, and we can recover nearly the complete key stream, except the first instruction, which is still missing, but it can be guessed. It's just a load of the machine status register. Yeah, it's now possible to build a device which replaces the original ROM chip using a CPLD and a flash memory, which manages the protocol of the ROM and inject own code, which is properly encrypted. We know the key stream, we can encrypt our own BIOS, and this BIOS can boot its own stuff much more quickly than the original solutions. It involves modifying the hardware and it involves implementing a board, but yeah, we have built such a replacement. We call it the IPL replacement. The IPL is the initial program loader, another name for the BS and BS2 for the boot ROM. However, represented here, it will be completely open, including all the software running on the cube, the schematics, the VHDL code, and all tools. It will be completely open in the hope that there will be some scene which actually programs stuff for the GameCube, because it's now much easier to program for the GameCube. It doesn't help pirate guys because they still can't boot their burned CDs. It's the DVD firmware which prevents the boot of the burned DVDs, and we won't modify the DVD firmware. So it's really only for homebrew code, but it can boot in homebrew and executables in seconds and not in 2 minutes like the original solutions. It has, of course, an option to be invisible after boot, so you can boot the games as well as like before, and it could also implement additional features like a serial port for debugging or something, because a normal GameCube doesn't have it, and it makes development very complicated without it. Okay, now Rob will tell you a bit about extending the GameCube, and then Michael will tell you about the GameCube Linux.
So we want to extend the GameCube hardware. Why do we want to? Because we can use the GameCube as an embedded computer. For examples, home automation, your cinema set, to make a car infotainment system. But we need some hardware which lacks from the original GameCube. We have no data storage. We want a hard disk or a flash drive or something. We can't hook up a mouse or keyboard, which is quite difficult while debugging. We want some generic I/O, like flashing LEDs or putting on relays and lamps and stuff. And we have only 14 megabytes of RAM, and that is the main RAM and the auxiliary RAM together, which is not sufficient for a lot of applications. So we need a hard disk interface, a flash storage interface, a RAM extension. We could very well use a USB interface, so we could hook up all kinds of other devices. Keyboard and mouse would be nice, and we want some generic I/O. So what do we have available? We have on the front of the GameCube 2 memory interfaces in which you usually put your memory storage cards. They are called EXI interfaces, but in fact they are standard SPI interfaces. So with a clock signal, a chip select a data in from the memory card to the GameCube, and data out from the GameCube to the memory card. We have 3.3 volt and 5 volt power available, so we can power our stuff we hook up to it. And which is also nice, the connector is etched on the PCB of the memory card, so we don't need to buy or find or make a special connector. We just etch our own PCB with the connector on it. And what can we do with it? The SPI, it's a very standard protocol. It can very easily be interfaced to, for example, a shift register IC, which you can use for general digital input, output, or perhaps you use a ADC or DEC for analog input and output. What we have already implemented is an interface for secure digital and multimedia cards. They are also, you can also use them in SPI mode, so that's very nice. As you can see on the picture, it's only a matter of hooking up some wires from the SD card to the memory interface. It's nothing more. We could also make, with a little logic, for example, a CPLD or something, a host controller for USB 1.1. USB 2.0 won't be possible because of, in fact, two reasons. First is that we do not have the bandwidth on these interfaces, and also USB 2.0 host controllers are only available to interface with a PCI bus, which makes sense because that's on the place where they are normally used. But it would mean we would have to interface a PCI bus to the Gamecube and then add a USB 2.0 controller. So that won't be really feasible. Then other interfaces we can use, the serial interfaces, which are normally used for the controllers. We have 4 of them. They are one wire interface. It's an open drain bus with some custom protocol, but it's very easy to monitor it on an oscilloscope or logic analyzer or something. And its speed is low enough to just bit bang it with a standard microcontroller. And then if you have that microcontroller connected to your Gamecube, you can use any hardware which you want to connect to it, like a UART, digital I/O, analog I/O, whatever you want. Then we have the high-speed interface. The high-speed interface is on the bottom of the Gamecube. It is an SDRAM interface. It's meant to add SDRAM or add other devices like the Game Boy player, with which you can play Game Boy games. It's a standard SDRAM interface, so it means you can just hook up any SDRAM chip. The pinout and all the stuff are documented in the patents, so you can just solder it to it. But the software side is a bit unclear, so we don't know yet which would, for example, be the maximum RAM size. And then we have, as last interface, the DVD interface. It's, as you can see, on the inside of the Gamecube. This is the Gamecube with the DVD drive removed. It's an 8-bit interface. It's bidirectional, and you can use DMA on it with a DMA completion interrupt. So with CPLD or something, you could hook up an IDE hard disk drive, but it won't be, well, with simple hardware, it won't be compatible with the original DVD drive, but it wouldn't really make sense because, well, we write our own code, so why do we want to have compatibility with the original DVD drive? We could just keep it simple and write our own code to interface this hardware if we are going to build it. It does mean we can't use the DVD drive anymore, so it's only for Gamecubes with a mod chip and only, so an IPL replacement, and it's only for Gamecubes which will not be used for games, but just as an embedded computer in whatever application you want. A problem here is that the connector, it seems to be custom made, or it's hard to find. we have not come across a suitable connector yet. So, well, you could desolder it from the DVD drive, but it's kind of tricky. So, our hardware extensions which we want to make. The hard disk interface, it can be implemented on the DVD interface. The flash storage, we have the secure digital card, which we will show on the end of the presentation. We can make a RAM extension on the high-speed interface. We can make a USB interface. A keyboard and mouse controller are available through the SI controller interface, and the same applies for the I/O. So we have for every required hardware extension which we want for the applications named in the beginning, we have a suitable hard disk hardware interface available. So that would mean, well, we could use our GameCube with some hardware modifications for all those purposes. Well, so far the hardware part. Now Michael will tell you about the Linux part.
Hello, my name is Michael Steil, and I want to tell you about Linux on the GameCube. The first question is, who are we? Who ported Linux to the GameCube? It's all the GameCube Linux project on the internet, gclinux.org. Basically, it has been started by the same people that did the Xbox Linux port. But we didn't, well, because all those people did the Xbox first and the GameCube afterwards, we were a bit late on the GameCube, so we didn't really hack the GameCube, we merely implemented all the stuff that had been known before. For example, Felix had done a lot of reverse engineering before we actually started with porting Linux. So why would it make sense to have Linux on the GameCube? Of course, hacking is fun, but well, the GameCube is silent, small, and cheap, and with Linux you can get the maximum flexibility of any device. So there are 4 examples of what you can make with a GameCube with Linux on it. The first possibility is you can either use it as a real PC, because it has quite powerful hardware. Well, it's just 40 megabytes of RAM, that's a limiting factor. But perhaps with some hacks you can get KDE or GNOME to run, or if you don't want to run the real operating system and the real interface and everything, you can also use the GameCube as a thin client with VNC, remote desktop connection, X window forwarding and all this. And it's all on a TV. The second possibility is you can use it as a media player, for example play DivX or MPEG or MP3 from the network. Or, well, you can use it as a server. It's 486 megahertz, which is quite powerful, and it's a power PC. It's not standard x86 hardware. It's another architecture for those who are interested in power PC servers. And the fourth possibility I personally came up with is the one that I find most interesting. It is not necessary anymore to port emulators to the GameCube platform, as many people have done, or port games, port the GPL's Doom engine to the GameCube. It's just porting Linux and then just apt-get install and run all the standard software that is available on the Linux platform. Well, and there's yet another motivation, that is, there must not be any closed platforms. We've done it on the Xbox, we freed the Xbox, so it had to be done for the GameCube so that people can work with their hardware that they have bought in a way they want it to work. For all this to work, we have heard that Nintendo has made some mistakes. There are flaws in the system, so we could start porting Linux and developing some drivers. I want to tell you about the drivers in detail, what drivers there are, what they can do, and some interesting details about them. Well, the interrupt controller is one thing that is incompatible with the standard. Well, it's a power PC. The Xbox is a PC, but the GameCube is not a Mac. The GameCube is custom hardware. So we couldn't just use all the drivers that existed. Interrupt controller is different. The frame buffer is this weird ArtX thing. It does not use RGB, it uses YUV, which is quite tricky because with this different color space, all colors would be off. We had our own color space converter, but MPlayer, for example, or X-Window just don't use the put pixel functions we provide in the frame buffer driver, but think, hey, cool, there's frame buffer, that's certainly RGB, let's write into it, and everything is pink. That's weird. I think black really gets to pink and white gets to green or something. So a lot of software had to be patched. 3D acceleration is something we're still working on at the moment, and this looks quite promising because reverse engineering works quite well there. We're having a gamepad controller, which is quite straightforward. Keyboard, the keyboard driver was also a bit tricky. There is one keyboard from Sega, because Sega released Phantasy Star Online, the only game with a keyboard, and released the keyboard for this specific game. And there are also from Datel and from Lixang 2 different adapters for PS2 keyboards. But the standard keyboard from Sega is not a PC keyboard. It doesn't have an Alt key or a Windows key or something, but it's very different. So they try to map the keys, and both companies map them very differently. So it's quite a problem for the keyboard driver. There's also the broadband adapter, which has the problem that it can do 100 megabits, but the whole bus system cannot do 100 megabits, which it's connected to. So we had to limit the broadband adapter to 10 megabits, which works quite well. Well, the adapter works, but it's a bit slow. Felix has told you about ARAM, 16 megabytes of additional RAM, which the CPU cannot directly address, but the sound hardware can, for example. So we have an audio driver which uses ARAM, and we also have a block device which accesses ARAM. So you have just a block device of these 16 megabytes minus some space for audio. And you can do anything with this block device. You can format it as a device, as a file system, or you can use it as a swap device. Using it as swap means you have effectively 40 megabytes of real RAM. Furthermore, we have a memory card adapter. Memory cards on the Gamecube are only up to 2 megabytes, so this is not really interesting storage, but, well, you can copy save games then. The SD card adapter by Rob also has a driver which still needs some work, but it looks quite promising, and SD cards are available in very big sizes, so we can finally be independent of network booting and all this. Yeah, and there's also there's a missing the SRAM and RTC, well, the real-time clock driver. So what does this look like in practice at the moment? If you want to use the Gamecube as a computer, yes, you can run X-Window, and yes, now the colors are okay. You can use KDE and GNOME, but, well, you really do have memory problems. The best thing what you can do is remote desktop, X protocol, VNC, REC, which works really perfectly. As a media player, the Gamecube is powerful enough to play full-screen DivX and practically everything that is out there which is not HD TV. As a server, you can install any full Linux distribution. You just put it on an NFS server, put the kernel through some hack, hardware hack or PSO hack into the box, and it mounts the NFS share and works just like any PowerPC Linux system. You can also use all server software if your memory is enough. One thing we have done is we have run the full PostgreSQL regression tests, and it worked, which shows that it works as a server. For games and emulators, 480 megahertz and 40 megabytes of RAM is enough to emulate old classic systems like MAME and SNES 9X, all these emulators run. But the emulators must use the SDL libraries and not access the screen directly, or the colors will be off again. What is possible is to bundle the emulator and perhaps some emulator images or games into one init.rd, so you don't have to have a real file system from network or from SD card. You can just load everything into the GameCube and then it's standalone. But there are problems, what we don't have at the moment and what's not so easy. For example, if you want to use it as a server, if you want to play media and all this, you must have networking. You must buy the network adapter, the broadband adapter, which is not so cheap and which is not so easy to find, because practically it's only produced for one single game, Phantasy Star Online. So the root file system, media, everything is on the network, and network only has 10 megabits. But this, we're working on this solution, which is practically the SD card interface. So you can put your whole Linux distributions, you can put your media, everything onto SD cards. And with further interfaces like hard disk and USB and what else we're thinking of, this won't be a problem in the future. Furthermore, there are very few ready-to-use solutions. At the moment, you have to compile your kernel or download a kernel perhaps, and it's a lot of fiddling around at the moment. We don't have pre-built images for SD cards or so, which can boot into an emulator or something. But this is just a problem of doing software development. And which is still a problem is booting the PSO hack just takes some time. We'll show you the PSO hack. You have to go through the menus. You have to select yes, new game, yes, I want to connect to the Sega server, which I don't. This takes a lot of time. But also, as Felix told us, there's the IPL replacement. It requires a bit of soldering, but then the GameCube is really free and you can boot anything directly from the ROM. Okay, I think we'll show you a bit now.
This is not the correct resolution, but I don't care. Okay. Okay, it's not. Sorry about this, but I think, okay. I will now boot a GameCube which has this IPL replacement installed, so you won't see the usual GameCube startup, but in fact, yes, a simple screen. Okay, you don't see anything. Okay, that's a good question now.
Speaking of questions, we can bridge this gap perhaps with questions.
Rumor has it that the DVD drive is actually a drive which is not like a standard DVD or CD drive operating with constant linear velocity, but with a constant angular velocity, providing seek times of a hard disk, or similar to a hard disk. Can you tell me anything about this?
Okay, basically the DVD is, the data format is proprietary. It has a proprietary sector layout, but the technology is still DVD, so I think the question of CLV and CAV is only a question of the DVD drive itself. So yes, the data will be layouted so that the data at the outside of the disk is read much faster than on the inside. But the DVD is still a usual DVD, so with a patched firmware, for example, it can be read on any usual DVD-ROM on a PC. Sorry.
Well, but I think it would be quite difficult to find a patch for a standard DVD drive to support this kind of sector layout.
Yes, but the sector layout is still like a normal DVD. There are some bytes which are not on their position, but and it's encrypted as well. Yes, but the recording format is the same as on a standard DVD.
Okay.
Sorry, I'm not able to answer your question. Really, sorry.
Okay. But I do have another question regarding the Triforce device. You might know this is a standard Gamecube with hardware from Sony added and a toolkit from Sega to be put into arcade machines. Does this kind of hardware have any relevance to your project yet? And if so, can you tell us about it?
No, I know about these devices. They have 48 megabytes of RAM, and otherwise I think they are more or less identical to a Gamecube, I think. But I've never seen such a device, sadly.
Well, supposedly it had hardware from Sony added to, I think, improve graphics capabilities, but I'm not sure now.
Yeah, I don't know how they could improve the graphics without replacing the whole 3D engine. It might be they might did this, but I'm not sure. I have never seen such a device.
I have one question about the SD card interface. Is software for completely open source? Because I remember to get the SD card specification, you needed an NDA and the like, and that was the reason no SD cards can be used on Linux on the iPad, for example.
Sorry?
Here, okay, here. Is the SD card interface driver completely open sourced?
Yes.
Oh, okay.
It's just available at our website in the CVS. So.
Okay.
Looks well enough. Okay, it looks like the picture is not really perfect, but perhaps you can see something. Green, green, green.
Waar kan ik wel wat zien?
Green, green, up green.
Okay, this is now the PSO game method. Wait, I have to fix up something. So, as you see, it takes quite a time. Each time you want to load your own code, it's now the game goes through all the initialization sequences and stuff. Linux, at last, the upper half of Linux.
It's booting, and if we're lucky, it's mounting NFS and loading init from NFS and showing us something.
Oh, it's all okay.
As you can see, this is a standard DivX, and it has no problems reading it from an SD card. There's an 100 megabyte SD card in the Gamecube at the moment with our adapter, and it reads the video and plays it. Normally it should be 640 by 480, but it's more like anything by anything at the moment. Ich glaube, mehr können wir nicht
Alles klar. Okay.
Okay, I think our time is up. We're sorry we could not answer more questions, but we will be available for you right outside the door if you want to meet us. Or we also have a table at the Hack Center. Just ask the people for us about us. You'll find us. Thank you.